We're going to be using the document camera a lot today, and so what I'm going to actually do is I'm going to switch over from the from my screen to the document camera. If at any point there's an issue with being able to see the document camera, just type in the chat and let me know. But then I'll go ahead and put up the DocCam screen. And so for a lot of today, I printed everything out just so that we could work through it. And if we take a look at the do now, again, 1, 2, and 3 are these multiple choice review type questions. So for number 1, for irreversible chemical reactions, so that means you have reactants going to products. So for irreversible chemical reactions, the reaction rate will be affected by changes in all of these except. So it wants us to figure out which of these will not affect reaction rate. So yesterday, we talked about temperature affecting reaction rate. We talked about concentration of reactants. Remember, reaction rate is all about collisions between reactants. Right, collisions between reactants. So concentration of reactants, if that changes, reaction rate changes. We talked about a catalyst. We didn't really talk about products, so we'll come back to that one. And we also did talk about surface area of a solid, so we looked at the powder versus the pellet. So the one of these that is not going to affect reaction rate is the concentration of products. So 1 is D. Right, products don't affect reaction rate, only the reactants, because it's collisions between the reactants. For number 2, if the temperature is increased, make it a little bit clearer for you. If temperature is increased, the reaction rate is, so as we increase temperature, if we think about it in terms of collisions, you increase temperature, you increase the motion and the energy of the particles, you increase the number of collisions, so you increase the reaction rate. Number 3, with all else being equal, so concentration, temperature, right, everything else being equal, a solid sphere in a liquid will react faster than 2 liquids. So if you actually look back at the first page of your notes, it actually says that the homogeneous, so if we look back at homogeneous versus heterogeneous, right? And it says that one reacts faster than the other. So the more collisions, the better. So homogeneous actually reacts faster because there's more contact. So for number 3, that's going to be false. 2 liquids will actually react faster than a solid in a liquid. Okay, and then number 4. So number 4 is where the math, this is looking at a question like yesterday where we looked at the stoichiometry. So if the rate of disappearance of NH3 is 18 molar per second, so the rate of NH3 is 18 molar per second. Remember that reactants disappear. So when it says rate of disappearance, rate is always given in positive values, but disappearing means it's a reactant, appearing means it's a product. So it wants to know what are the rates of the other reactants and products, then note if they're appearing or disappearing. So based on NH3, we're going to look at the factors like we did yesterday to solve for these other ones. So I'm going to start every single time with NH3, and I'm going to go to each of my other substances. So if I have 18 molar per second of NH3, let's start by going from NH3 to O2. So for every 4 NH3 that react, we need 7 O2 to react. So remember, when you're looking at rate of appearance and rate of disappearance, we use the stoichiometry because this is average rate. So for average rate of appearance and disappearance, we can use the stoichiometry. So 18 times 7 divided by 4 is 31.5 molar per second. Again, this is a reactant. So this is disappearing. Right, so here's O2. So I'll label O2 up here. So oxygen, O2, is disappearing at a rate of 31.5 molar per second. Has a higher coefficient than NH3, makes sense that it has a higher rate. Now, I could set it up, but I know I'm going to run out of space, so I'm just going to focus on the coefficients here. NH3 has a coefficient of 4, NO2 has a coefficient of 4. Same coefficient, same rate. So NO2 has a rate of 18 molar per second, but this is appearing because it's a product. Products appear, reactants disappear. So then I'm going to start with NH3, and you could really start with any of them. NH3, now that we know O2 or NO2, to go to H2O. I'm just going to start with NH3 since they already gave that to us. So 18 molar per second of NH3. Again, I'm going to use the coefficient. So for every 4 NH3 that reacts, we form 6 H2O. 18 times 6 divided by 4 is 27 molar per second. And again, that's appearing. And that's H2O. All right, so each one of our reactants and products are appearing and disappearing at different rates because it's based on the stoichiometry. If we wanted to look back yesterday, like when we were looking at the reaction, I'm going to actually kind of write it up at the top of this slide just so that we can look at it. But if I want to actually look at the overall reaction rate, it's actually going to be a little bit different. So I'm going to start with NH3 again. Again, this isn't part of the question, so I'll go back down to the bottom in 1 second. So if we want to look at the overall reaction, 18 molar per second of NH3. Again, based on the balanced equation down here, for every 1 time this reaction runs, all right, if this reaction runs 1 time, it uses 4 NH3. So I could actually set up my factor like this. So 18 divided by 4. So the overall reaction has a rate of 4.5 molar per second. The overall reaction, if I wanted to know how the overall reaction rate is changing, it'd be 4.5 molar per second. Again, we're going to tie this in a little bit today as we're looking at overall reaction rate, and then we'll actually tie it back into appearing and disappearing. So that's if we wanted to look at overall reaction rate, because every 1 time the reaction runs, we need 4 NH3s. And you could have used any other one as well. And so here's everything if you need to copy down on your do now sheet. I'll give you just a second, copy everything down. Okay, so that was it for the do now today. So really we just had do nows 3 days this week. We'll have do nows each day next week as well. As always, as we're going through examples today, if there are questions, please type them in the chat. I will be going back and forth between the document camera, like between looking at my document camera and flipping back to the Google Meet. Because this is new, I can't see any confused looks like I usually could in class to try to go back over things again. So if you have questions, just make sure that you type them in the chat. If you go back and you watch this recording later and you think of other questions, feel free to send me a remind, email, anything like that. So as we are getting into kinetics today, we will be going through some examples in the notes. We'll be doing additional things in the notes as well, which is why I said you want to make sure that you have them ready to go. So as we start off class today, we're actually going to go into page 7 of the notes. So in page 7 of the notes, you have this summary table. So if you flip in your notes to page 7, you have this summary table. I'll show you what it looks like on your notes page. All right, it's kind of right here in the middle of page 7. Right, it looks just like this. We're going to be filling this in together, and we're going to be adding extra information. So I'm going to try to answer questions that you had from the video as we go through and we fill in this summary table. So what we're going to be looking at today is we're going to kind of switch gears from what we did yesterday. Yesterday we looked at average rate. So average rate is like slope. It's change in concentration over change in time. What we're going to focus on today is we're going to look at how we can study the effect of concentration on rate. But more specifically, we're going to look at how we can look at how initial concentration affects initial rate. And so to do that, we create what is called a rate law. So as we go through this, again, I'm going to add more information as we're looking at this table. You can feel free to add it in your notes as well. But with this summary table, this is looking at rate laws. So the first thing that I want to focus on is just a quick review of rate law again. Right? What is it? Why do we use it? So a rate law shows how the rate depends on concentration. So the rate law shows how the rate depends on the concentration, and more specifically on the reactant concentration. So it shows how rate depends on reactant concentration. This is a way that we can calculate initial rate based on concentration of reactants. So we're not looking at a change over time like we were in the first video. We're looking at initial rate. So as we're going through and we're creating rate laws, we're going to talk about reaction orders. So when this is asking about overall reaction orders, that's going to be the sum of the individual orders. Now, reactant order is simply exponents. The reactant orders are given by the exponent of the concentration. So overall means we're adding up the exponents. We will focus more on reaction order as we go through these examples. And then for units of the rate constant, to find the units of the rate constant, we just have to plug in information into the rate law. So your units of your rate constant will change. Right? Your units for your rate constant change based on the order. It's not always the same. And rate constant is represented by a little k. Now, I do want to point out one thing. There was a typo on one of the questions in the video. Both temperature and catalyst affect the value of the rate constant. So I think that it was one of the check mark boxes, and temperature and catalyst should have both been checked. So both temperature and catalyst affect the rate constant. That's it. If you're only changing concentration, the rate constant stays the same. It's a constant, but the only thing that can change the rate constant is temperature and if you're changing a catalyst. So as we're looking at this summary table, we notice that they give us rate laws. So rate law is always rate equals K times the concentration of reactants. So in this first example, they don't give us any reactants. Well, if you think about this, if I had A, right, we're assuming that A and B are the reactants here. If you have A or B to the 0 power, that's a 1. Right? Like that's actually the numeric value 1. So if there is no reactant in here, that means it's 0 order. Right? So this is 0 order. Now I'm going to do a quick overview of each of the orders as we go through. Zero order means that rate is independent of the reactant concentration. So you're going to notice I'm going to use brackets a lot to simplify concentration, just so I don't have to write out concentration. So since there's no reactant here, it's probably to the zero order, because a to the 0 is 1, and 1 times k is k. So since there's no reactant here, the overall reaction order is zero order. Now, we're going to look at rate constants in a second. We're going to look at how we can actually calculate or determine the value of the rate constant. So looking at this next one, rate equals K times the concentration of A. Well, remember, if there's no number there, it's assumed to be a 1. So the overall reaction order is just adding up the exponents. And you're only focusing on the reactants, not K. So my only reactant here is A to the first power. The only exponent I have there is 1. So this is a first order overall. Now, first order reaction means that rate is proportional to concentration. Again, we're talking about reactant concentration, not products. Products do not matter. We don't care about products. It's only based on reactants. So what I mean by proportional is let's say that this starts at 2 molar. If I double this concentration, I'm also going to double the rate. It's exactly proportional. Whatever you do to the concentration, you will also do to the rate. So then let's look at this next one. Rate equals K times the concentration of A squared. My exponent is a 2. The only exponent I have here is a 2. So this is second order. So a second order reaction. And usually second order is where questions start coming in. But this is when rate is proportional to the concentration squared. So here's what that means. If I double the concentration of A, right, 2 times as much. So if I double it, 2 squared is 4. The rate is going to increase 4 times. It's going to quadruple. Or if I triple the rate, right, so if I triple the rate, I'm changing it 3 times. 3 squared is 9. The rate will increase 9 times. So that's what we mean by proportional to the square. And we're going to look at actual examples of determining the rate law. So then if we look at this next one, rate equals K times the concentration of A times the concentration of B. So remember, if there's no exponent there, it's assumed to be a 1. Add up your exponents. 1 plus 1 is 2. So we would say this is second order overall. And then for this last one, rate equals K times A squared times the concentration of B. And if there's no exponent there, it's assumed to be a 1. So 2 plus 1 is 3. So we would say this is third order overall. Right? And then you could see we're only really going to ever focus on individual reactant orders being 0 first or second. We might see a third order overall or a fourth order overall. Essentially what that means is now every time we change the rate, whatever the overall reaction order is that exponent. So like third order, for example, the rate is proportional to the concentration cubed. So let's see, if I double the concentration, 2 cubed is 8. The rate will increase 8 times. Right? And so that's how reaction orders will change. Now with rate constant, the units for the rate constant are different based on the overall reactant or reaction order. So think about just plugging in your values. So it says up here, assume the units for rate are molar per second. So if I look over here, if I were to plug in just units, not even numbers, well, remember anything to the 0 is 1. So if rate is molar per second, and that equals K, Our units for K are molar per second. That's when it's zero order overall. First order, so let's just plug in units. Rate equals K times the concentration of A. So rate is molar per second equals K times concentration. Remember, concentration is molarity. Now, if I solve this for K, I need to divide both sides by M. All right, notice your molarities cancel over here. If you have two numbers cancel and you have something on the bottom, that would be like 1 over. So if it's first order overall, the units for your rate constant is 1 over seconds, or you might see it represented as s to the minus 1. We would call that a per second. And you could then do the same thing. So second order, let's look at this one. Rate equals K times the concentration of A squared. Rate is molar per second equals K times the concentration of A squared. So concentration is molarity squared. Solve for K. So that would be molar per second divided by M squared. So if I divide both sides by M squared, reduce this. One of the molarities on the bottom will cancel, the one on the top will cancel. You get 1 over molar times seconds. 1 over molar times seconds. Or you might see it written as per molar per second. That means the same thing. The minus 1 means it's in the denominator. So anytime you see a second order overall, it's going to be the same thing here. Molarity times molarity is molarity squared. M to the minus 1, S to the minus 1. Notice how here, every time you're adding a molarity on the bottom, because here it's 1 over seconds, 1 over molarity times seconds. If it was third order overall, it'd be 1 over M squared times seconds. Or M to the minus 2, S to the minus 1. And again, you can do that by just plugging in your units, and we will look at that more and more and more as we go. So again, the whole point of these orders, the whole point of looking at these orders down here, we remember that order determines how rate is affected by concentration. So the reaction order determines how the rate is affected by the concentration, or is it affected at all? So that's the summary table that's on page 7 of the notes. Let's see. So exponents, like up in the rate law, we're actually going to be determining that like in some of these examples. So the exponents here, like for this rate law, our exponents, like they just gave us these rate laws. In some of these examples, they're just giving us the rate law. We actually have to determine them experimentally, and we will look at some of the examples as to how we can actually determine it experimentally. We'll actually look at the data and how to tell. So we'll actually look at how to determine each of these exponents. Okay, so any other questions? Is the screen not working well? Okay. It may have been because I was like flipping back and forth quickly between the dot cam and the Google Meet. It was kind of flashing for a second, yeah. Okay, so that's it for the summary table. Again, if there are other questions, you can feel free to send them in the chat, send them in Remind. I have Remind open on my other computer as well. So what we're going to do is we're going to actually look at this video example. So in the video in 5.2, I kind of left you with this example and I said, try this. This will be the first thing that we talk about. So in this example, this says what are the individual and overall reaction orders for the reactions described. So in this example, they give us an overall balanced equation. They also give us the rate law. So to go off the question on where do these exponents come from, we have to actually determine them unless they give us that information already. So when we're looking at the individual and overall reaction orders, it always comes from the rate law. We do not ever look at the balanced equation for reaction orders. We only look at the rate law. So when we look at the rate law for reaction 1, the rate law is rate equals K times the concentration of N2O5. Notice how the rate law does not necessarily match the equation, and that's okay. It usually won't. So what we're going to do is we're going to use the rate law to determine the order. So what we would say for N2O5, we look at the exponent, right? If there's no exponent up here, it's assumed to be a 1. So we would say N2O5 is first order, because whatever the exponent is the order of reactant. Then overall, add up the exponents. Well, there's only one exponent. So overall, the reaction is first order. So N2O5 is first order because it has this coefficient, or this exponent. And then overall, you add up your exponents, but we just have the 1, so it's also first order. Reaction 2, again, they give us the rate law. We have to use the rate law that is given, not the balanced equation, not anything else, but the rate law. And the rate law has to be determined experimentally. We're going to look at how we determine that experimentally in some of the examples. So in reaction 2, rate equals K times concentration of CH3CL3 times concentration of Cl2 to the 1/2 power. So if we take a look at this, CHCl3 and Cl2, we have 2 reactants. All right, only reactants will be in the rate law. CHCl3 doesn't have an exponent up here, so it's assumed to be a 1. So CHCl3 is first order. Cl2 has an exponent of 1/2. Now, we don't usually see fraction orders, but we've seen it in the multiple choice before. So we have seen it in the multiple choice where it gives us a fraction, but it already gives us that exponent. So we would actually say Cl2 is 1/2 order. So just identifying that that exponent is the order. And then overall, we would say the reaction is, add up your exponents. 1 plus 1/2 is 3/2 or 1.5. So we would say overall, the reaction is 1.5 order. Now, is that common? No, but we have seen it before. So that's the video example that is from the bottom of page 7. All right, so the bottom of page 7. That's just using the exponents to determine the order of each reactant. But what we're going to do is look at how we actually can determine the rate law experimentally, because that's the only way that we can write a rate law, is to use data. Okay, any questions on this example? Okay, so if not, we're going to go ahead and we're going to flip to page 8 in the notes. So I'm going to actually flip over to the notes as well. So I printed out the notes packet so that I can work through it. Now, I don't know if you realize this or not, maybe not. This is the second example 6. I was going to retype all of the questions or all of the numbers, and then I realized that some people already had the notes, so I just left it. So there are 2 example 6s, but that's okay. So for this example, this is a reaction. A plus B yields C, obeys the following rate law. So notice how, again, they gave us the rate law. So something that I'm going to kind of make note of over here is that the rate law must always be determined experimentally. Now I say experimentally like we have to use data, and we will be doing that in some of the examples just a little bit later today. More than likely what they already did is they already used that experimental data to figure out what the rate law is for us, and they just gave us the rate law. So looking at this problem, right, they give us the rate law. Another thing I want you to remember is that the rate law is always rate equals K times the concentration of reactants. So only the reactant concentration matters in rate laws. Right? Only reactant concentration matters. So if we take a look at this, it says if the concentration of A is doubled, how will the rate change? And will the rate constant change? So what I want us to look at is if we take a look at this rate law, it says if A is doubled, the rate law tells us how the rate changes based on the reactant concentration. Right? So the first thing that I would ask is where is A in the rate law? Right? And I'm writing these questions just so that way if you're looking back at the examples, that can be something that you ask. So where is A in the rate law? Well, it's not there. Rate law is right here. Don't worry about this equation, the balanced equation. Balanced equation only tells us what our reactants are. This rate law is what we use to figure out how the rate will change based on the concentration. There is no A here. I could increase A's concentration by 1,000. A is not here. So if A is not in this rate law, rate's not going to change. So I'm going to say there will be no change in the rate because A is 0 order. Right? And I'll in parentheses say not in rate law. A is not in the rate law. So A will not affect the rate. Only B will affect the rate. Now the second part says, will the rate constant change? So I'm going to say K will not change. Now K never changes if you're changing concentration. So something else that we can write over here off to the side, right? These are just some things that we want to remember, is that rate constant, which is K, is only affected by temp or a catalyst. So temperature change and a catalyst is the only thing that ever changes the value of the rate constant. Changing reactant concentration doesn't matter. It's a constant. K is constant unless you change temperature or a catalyst. So part B says, what are the reaction orders for A and B? What is the overall reaction order? So reaction orders for A and B. So we're looking at individual, right? A is not in this rate law. That means it's zero order. So A is zero order. Right? And sometimes you see it written as the reaction is zero order in A. That means the same thing. Then for B, B is in the rate law. So look at its exponent. Its exponent is a 2. So B is second order. Right? Or the reaction is second order in B. So overall, add up these exponents. Add up these two numbers. 0 plus 2 is 2. So overall, the reaction is second order. So the orders always come from the exponents in the rate law. They gave us the rate law in this problem. So they told us already what the rate law is. We didn't have to figure it out. Finally, for C, what are the units for the rate constant? So let's plug in units into this rate law. So rate equals K times the concentration of B squared. So remember that rate is almost always given in molar per second equals K times concentration squared. Concentration is molarity squared. Then we can solve for K. So if I divide both sides by m squared, let's reduce where we can. So 1 molarity on the top, 1 molarity on the bottom. So it leaves us with nothing on the top and m times s on the bottom. Remember, nothing on the top means that it's a 1. So K is 1 over molar times seconds, or per molar per second. So to find the units for the rate constant, we can just plug in. So to find the units for the rate constant, we can just plug in the units that we know for rate and for concentration. Why does it give you the reaction? So it gives us the overall balanced equation so that we know that A and B are reactants. Or we will look in a little bit at appearance, disappearance, compared to one of the products as well. So it'll give us the balanced equation in case we need it for anything else. But for this, a lot of times with kinetics, it's so that we know that A and B are reactants. So that way we can tell, based on the rate law, A is a reactant, B is a reactant. So we would expect to see both of those in the rate law. Well, if we don't see A, that's because A is zero order. So the balanced equation helps to tell us what are our reactants, what are our products. Okay, so again, I know I'm writing a lot of stuff over here. This is usually what I add onto the board as we're going through examples as well. So I just want to make sure that everything is here for us as we're going through examples. So for number 7, so example 7 says the decomposition of N2O5 proceeds as follows. All right, so they're giving us that balanced equation again. The rate law is first order in N2O5, right? The reaction, so the rate law is first order in N2O5. So they're telling us the order of reactant. They're telling us what that exponent would be. And then it gives us the rate constant. So it actually gives us the value for K. Right, so this is K. Part A says, write the rate law for the reaction. What is the overall order? So I just want to note, I want to pay attention really quick that they give us the balanced equation. This balanced equation is only telling us that N2O5 is a reactant. The coefficients right now do not matter. if they did not give us this order of N2O5, we would have to use experimental data to figure it out, like we will in example 9. But they told us what the order is. So if we take a look at part A, so first thing, write the rate law. So remember, the rate law is always rate equals K times concentration of reactants. Now, this is the very general way we're going to fill everything in. So rate equals K is usually what we start with. Right? Rate equals K. Our reactant, we just have one reactant here, is N2O5. They give us, so they have told us the order of N2O5. It's first order. The exponent is a 1. Now, you don't have to put the 1. Some people like to put that 1 so that they remember that it's first order. If there's no number there, you assume it's a 1. So they gave us the information that we need. Here's the rate law. Right, there's our rate law. And we could plug in K. We could put 4.82 times 10 to the negative third in here. Or we could just leave it like this. Then it asks for the overall order. Right? What is the overall order of reaction? Overall, the reaction is, we only have one exponent here. So overall, the reaction is first order. So overall reaction is first order. So now part B says, what is the rate of reaction when the concentration of N2O5 is 0.024 molar? So now we're getting into some math. Right? What's the rate of reaction? So it wants us to actually solve for rate. When you are solving for anything, rate, concentration, you always use the rate law that is given. So we just wrote the rate law. So we have to use rate equals K times N2O5 to solve for one of these unknowns, solve for one of the variables. So they gave us the concentration of N2O5. They also gave us K. We can solve for rate. So rate equals K is 4.82 times 10 to the negative third per seconds. Again, they gave us the rate constant. Concentration of N2O5 is 0.0240 molar. To the first power is just this number. Again, it's to the first power because we have to use the rate law that we just wrote. It's first order with respect to N2O5, which means it's going to be first order the entire time. This exponent will not change. So now we can plug this into our calculator. 4.82 times 10 to the negative third times 0.024. I suppose 3 sig figs. 1.16 times 10 to the negative fourth. So by using the rate law, we can actually plug in concentration and figure out what the rate would be. Right? What would the initial rate be? Now, if we look at our units, we have molar times per second. So that's molar over seconds, which is what we expect because rate is given in molar per second. So when we're calculating for rate or for concentration or even for K, we use the rate law that we were given. The rate law lets us compare, right? The rate law lets us compare rate to concentration. It's a way that we can calculate what the rate would be if we change the concentration, or what the concentration would be if this is the rate that we would see in lab. Now, part C says, what happens to the rate when the concentration of N2O5 is doubled? So there's two ways that you could solve this. The first way that you could solve this is that you could plug in 0.0480 molar to the rate law. Because remember, if all you're changing is the concentration, K does not change. The rate constant only changes if you change temperature or a catalyst. Right? K is still 4.82 times 10 to the negative third per seconds. So you could plug in concentration and K just like we did before, and you could calculate the rate. Or let's think about what it means for N2O5 to be first order. Remember, when a reactant is first order, whatever you do to the concentration, you do to the rate. So if we doubled the concentration, we double the rate. Right? We know that N2O5 is first order. So doubling the concentration will double the rate. And if you don't believe me, do 0.048 times 4.82 times 10 to the negative third, and I bet you're going to get double this number. And I know you will, because I did that calculation. So you could either plug in mathematically and solve for rate, or we can just use the idea that we know that N2O5 is first order. So doubling the concentration of that reactant will double the rate because it's proportional. Okay, so that's example 7. Let's go through example 8, and then we'll take a quick break just to give you time to stand up, move around. So example 8, consider the following reaction. So again, they gave us this reaction. It says the rate law for this reaction is first order in CH3Br. All right, first order in CH3Br and first order in OH minus. They gave us the order of each reactant. So again, if they didn't give us this, so if they didn't give us orders, we would need to determine it experimentally. So if they didn't tell us, hey, this is first order and this is first order, we'd have to determine it experimentally. So part A says, what is the value of the rate constant? And part B says, what are the units of the rate constant? So before we can do anything, we need to write the rate law. All right, I didn't even read ahead with the concentrations. The first thing we need to do is write the rate law. Then we can figure everything else out. So based on the information that they gave us, I'm going to write the rate law. Rate law is always rate equals K times concentration of reactants raised to whatever their orders are. So my two reactants are CH3Br and OH minus. So concentration of CH3Br, it says it's first order. That's an exponent of 1, right? Or you don't put the exponent at all, which is usually what I do. We put the 1 just to help initially. Times the concentration of OH minus, again, first order. So there's our rate law. Rate equals K times the concentration of CH3Br times the concentration of OH minus. The reason that they're both to the first power is because in this problem, they tell us that it's first order and first order. So they have already determined how the concentration of CH3Br affects the rate and how the concentration of OH minus affects the rate. So we're going to go ahead and just do A and B at the same time. This says when CH3Br is 0.005 molar and OH minus is 0.05 molar, The reaction rate is 0.0432. The reaction rate. So now in this problem, they're giving us the rate and each of these concentrations, and they're asking us to find K. So let's just plug everything in, and I'm going to plug it in with units as well so that we can solve A and B at the same time. So the rate is 0.0432 molar per second. That equals K times the concentration of CH3Br is 0.005 molar. Concentration of OH minus is 0.05 molar. We need to solve for K. So I'm going to start by multiplying 0.005 times 0.05. That's 2.5 times 10 to the negative fourth. So to get K by itself, I need to divide this over. All right, so again, to get K by itself, I'm going to need to do 0.0432 molar per second divided by 2.5 times 10 to the negative fourth. Molar times molar is molar squared. So numerically, we can find the value. We can just divide. 0.0432 divided by 2.5 times 10 to the negative fourth, 172.8. The higher the rate constant, the faster the rate. So the higher your value of the rate constant, the faster your rate will be. So K is, I'll just do 3 sig figs, 173. So there's our value. Now we can figure out the units here. So molar per second divided by molar squared. So this molarity will cancel. One of these will cancel. So if we put everything in the correct place, it'd be 1 over molar times seconds, or per molar per second. So there's A and B together. All right, A and B together there, because A wanted the value, B wanted the units. I just did it at once. Again, the higher your value of K, the faster your rate will be. So the higher the rate constant, the faster it'll go. Finally, part C. What would happen to the rate if the concentration of OH minus were tripled? So could you go in and solve for rate? Yeah, you could. Right here's K. Here's K. CH3Br, you could just triple OH minus, and then you could solve for rate. Or use the rate law. OH minus is first order. If it's first order, whatever you do to the concentration, you're going to do to the rate. So we can say since the rate law is first order with respect to OH minus, and I'm trying to write the wording in different ways so that way you can see how AP will ask it. They might say it's first order in OH minus. They might say it's first order with respect to OH minus. They might just say OH minus is first order. It all means the same thing. So since the rate law is first order with respect to OH minus, if the concentration of OH minus is tripled, the rate is tripled. It doesn't say anything about changing CH3Br, so we assume it stays constant. So whatever you do to the concentration of OH minus, you do to the rate, because it's first order. Okay, so those are the examples where they gave us the rate law. The next example, we have 3 more examples that we're going to do. This is going to look at how we can actually determine the rate law. And if you like problem solving, you'll like these types of problems. So I'm going to give you guys just a couple minutes. It's 8:25, 8:27. We'll continue on with examples. I just want to give you time if you need, well, it's 8:26. We'll do 8:28. I want to give you time if you need to get up and move around, go get coffee or something, just because I know it's a lot of going through examples today. So take 2 minutes, take a break, and then once you're ready, flip to example 9. Make sure you have a calculator. So take 2 minutes. All right, so again, we have just 3 more examples. Notice how this looks a little different. So example 9 says the iodine ion reacts with hypochlorite, which is the active ingredient in bleach, in the following way. They give us the equation. It says this rapid reaction gives the following rate data. So they give us 3 experiments with concentration of hypochlorite and the concentration of I-, as well as the rate. So in this problem, they're not telling us OCl- is this order and I- is this order. So what that means is we need to determine the order using this data. All right, so up here I'm going to say, right, we always need to use the data to determine orders. Right? They're not telling us, here's the order of I-, here's the order of OCl-. Instead, they're giving us data. So we're going to look at how we can actually figure this out. So what we need to do is we need to look at the concentration versus the rate for each reactant. Now, something that's going to be important to remember is that one of them must remain constant, and I'll look at what I mean by this in a second. So we're going to be looking at changing one reactant at a time, and we're going to look at how does changing that reactant affect the rate. So let's start, because notice how A says what's the rate law? Well, I don't know what the orders are. So I'm going to start by looking at OCl-, and I want to see as OCl- changes, how does the rate change? But in order to see how OCl- affects the rate, I need to make sure that I- stays constant. So if I take a look at this, I want to look at where OCl- changes, I- remains the same. So I'm going to look at experiments 1 and 2. Because looking at 1 and 2, I noticed that OCl- concentration doubles. So we go from 0.0015 to 0.003. Concentration doubles. I minus stays constant, which is good. You only ever want to change one variable at a time. So OCl minus, what I'm doing right now is I'm looking at how does OCl minus affect the rate. And in order to look at how OCl minus affects the rate, I need to make sure that I minus isn't affecting it either. So it needs to stay constant. So as OCl minus doubles, we need to look at the rate. Well, if you do 1.36 times 2, that's 2.72. So as OCl minus doubles, the rate also doubles. That means if it's exactly proportional, that OCl minus is first order. Now let's say you're like, okay, well, how was I supposed to know that 1.36 doubled is 2.72? You could go the other way, right? So here's what I would recommend doing. And I always tell people, if you have a calculator, to do this. 0.003 divided by 0.0015 is 2. So to go from 1 to 2, or experiment 1 to experiment 2, you're multiplying by 2. So do the same thing over here. 2.72 divided by 1.36 is 2. So to go from 1.36 to 2.72 is 2. So now let's take a look at I minus. Well, now I want to look at where I minus changes, but OCl minus stays constant, right? Only change one variable at a time. So I notice from experiment 1 to experiment 3, I minus changes and OCl minus stays the same. So from 1 to 3, I minus doubles. Right, we go times 2. From 1 to 3, the rate also doubles. So if whatever happens to the concentration also happens to the rate, that means it's first order. Now, I will always have people say, well, if I look at the balanced equation, it's 1 and a 1 for the coefficients. That does not matter. It doesn't always match up like that. You have to use the experimental data to determine the order. Remember that if it were 0 order, I could change the concentration, the rate would not change. First order, whatever we do to the concentration, we do the exact same thing to the rate. Second order would mean if I doubled the concentration, I would quadruple the rate. Those are usually the 3 orders that we will see. So the rate law for this reaction, so that's rate equals K times the concentration of the reactants raised to their order. So rate equals K times the concentration of OCl minus, right, it's first order, so it's going to have a 1, times the concentration of I minus, again, first order, it's going to have a 1. So the rate law is rate equals K times OCl minus times I minus. So then part B, what is the value of the rate constant? So to figure out the value of the rate constant, you need to pick one of the trials and plug in the values. Right, so pick one trial and plug in numbers. Because once you have the rate constant, you can plug in values and you can solve, or once you have the rate law, you can plug in values, you can solve for the rate constant. So if I'm just going to pick experiment 1, it's the first one. So rate is over here. Remember, I'm using this rate law. Rate equals K times the concentration of each. So rate 1.36 times 10 to the negative 4th molar per second. Rate constant, that's what I'm solving for. I'm solving for K. Times the concentration of OCl minus. So remember, I'm using experiment 1. Times the concentration of I minus. So now I'm going to solve. Now I'm going to solve. So to get K by itself, I need to divide both of these values over. So 0.0015 times 0.0015, 2.25 times 10 to the negative 6 m squared. That's what these two values are multiplied together. So right now I'm just solving for K. I'm moving everything over to solve. So 1.36 e negative 4 divided by 2.25 e negative 6, 60.4. So 60.4. And then think about units. One of the molarities cancels. So we have per molar per second. Notice how every time it's second order overall, our units are per molar per second. So whether you want to memorize, if it's 0 order, first order, second order overall, you can. Or you can just plug in your values every time. So then part C says calculate the rate. So you have to pay attention to rate constant, concentration. So calculate the rate when OCl minus is 0.002 and I minus is 0.0005. So again, once you have the rate law, everything goes back to the rate law. You use the rate law to calculate everything. Okay, so sorry, it's probably going to flash while I'm over here. So the rate law for the overall reaction isn't first order. Oh, yes. Yeah, sorry, I just saw your question. So like I'll just kind of answer based on this. So like OCl minus is first order, I minus is first order. Overall, it's second order because you're adding up your exponents. So each individual reactant has an order, and then the overall is when you add them together. So if we want to calculate rate, right, rate equals K times OCl minus times I minus. So for rate equals, remember K is the same, right? So K is 60.4, and then plug in your two concentrations. So plug that in and see what you get. How do I get this dude in here? So if you plug everything in, right, 60.4 per molar per second times 0.002, 0.0005. Right, remember, K only changes when you change temperature or you add a catalyst. Once you calculate K, it's the same because we're not going to be changing temperature yet. So then we can multiply these together. 60.4 times 0.002 times 0.0005. So when I plugged those in, I multiplied everything. I got 6.04 times 10 to the negative 5th. I suppose that's 2 sig figs, huh? Ugh. So we'll do rate is 6.0 times 10 to the negative 5th. If you notice here, one of the per molar cancels because molar over molar cancels. So you have molar per second. That's what rate should be. Rate is always molar per second. Also, it's going to match up what's in the table up here, right? Molar per second, molarity, molarity. So once you've calculated K, you have it the whole time. Okay, so questions on how we looked at this. I know this is totally different from what we've been doing, or maybe what you've done before, right? Kinetics is completely new. Using the data is the most important thing. You always have to use the data to determine the order of each individual reactant. So let's look at example 10. So example 10 says, consider the gas phase reaction between nitric oxide and bromine. They give us the equation. So we see that NO is a reactant, Br2 is a reactant. The following data for the initial rate of NOBr was obtained. All right, so this is the initial rate of formation of NOBr. So notice we're comparing concentration of each reactant to the rate. Part A says determine the rate law. So to determine the rate law, we have to figure out what are the orders of reactants. Because rate law is rate equals K times the concentration of reactants. So let's take a look at determining each one. So remember, one of them needs to stay constant. So if I look at changing NO, if I want to see how NO changing affects the rate, I need to keep Br2 constant. So I'm going to pick 1 and 2. Experiment 1 and 2. You could pick 3 and 4, but you need to pick 2 trials where Br2 is constant. So I see from experiment 1 to experiment 2, the concentration of NO increases 2.5 times. Again, if you're like, how do I know that? Well, just do this. 0.25 divided by 0.1 is 2.5. So if I do 0.1 times 2.5, I get 0.25. So NO increases 2.5 times. Okay, now, I can't do this in my head. So here's what I'm going to do. 150 divided by 24, that's 6.25 times. Right? So as NO increases 2.5 times, the rate increases 6.25 times. So let's just think through this. It's not 0 order, because if this were 0 order, if I increase this by 2.5, the rate would remain at 24 molar per second. All right, because 0 order means that whatever you do to your reactant, nothing happens to the rate. The rate doesn't change. So we know it's not 0 order. If this were first order, whatever I do to NO, I would do to the rate. So if I increase NO by 2.5 times, I would increase the rate 2.5 times. But I know that's not the case either. So let's think about what it means to be second order. Second order means whatever I do to NO, I do that squared to the rate. So 2.5 squared is 6.25. So whatever you do to NO, you do that squared to the rate. That means that NO is second order. All right, and this is a little weird because it's 2.5, but you might see something like 2.5. Right? If you double it, you'd increase the rate by 4 because 2 squared is 4. If you triple it and it was second order, 3 squared is 9, right? You'd increase the rate 9 times. In this case, you're increasing it 2.5 times. 2.5 squared is 6.25. So it's second order with respect to NO. So let's see how Br2 changes. So I use a different color, see how Br2 changes. So remember, I want to see where Br2 changes, but I need NO to stay constant because we can only have one variable changing. So I notice that's 1 and 3. So from 1 to 3, 0.2 to 0.5. Remember, we're looking at a factor. We're not looking at what we need to add. We're looking at what we're multiplying by. So again, I'm going to do 0.5 divided by 0.2. That's 2.5. So if I multiply 0.2 by 2.5, I get 0.5. So 24 to 60, right? I'm looking at experiment 1 to 3. 60 divided by 24 is 2.5. So whatever I do to Br2, I'm doing the same thing to the rate. that tells me that Br2 is a first order reactant. So for part A, determine the rate law. Well, I'm going to use this information that we just determined. Notice how we had to use the data to determine the order. You cannot use the balanced equation. You have to use the data. So rate law is rate equals K times the concentration of your reactants. So one of my reactants is NO, and we determined that NO is second order. Concentration of Br2 is first order. So again, if you want to put the 1 just so that you remember, you can. So there's part A. Determine the rate law. Rate equals K times the concentration of NO squared times the concentration of Br2. So that's our rate law. Part B says calculate the value of the rate constant for the appearance of NOBr. So pick one of the experiments. Calculate K. I usually just pick the first one because it's the first one. So to calculate the value of the rate constant, I'm going to use rate equals K times concentration of NO squared times concentration of Br2. You're using the rate law. Once you have the rate law, you're using that for everything. Again, I'm going to pick experiment 1 to use for part B. So I'm going to plug in all my information. So the rate, 24 molar per second equals K times concentration of NO squared. So 0.10 molar squared times the concentration of Br2. So notice I put the units in as well so that we can help to see what the units are. So if I want to solve for K, I have to divide everything that's over here over. So just be careful how you're doing the algebra. I'm going to put it in parentheses. So 0.1 molar squared, I guess I should say 0.1. Let's do this, right? 0.1 molar, that's squared times 0.2 molar. I guess put it in brackets. The reason I wanted to be careful with that is because when I plug it in, I need to make sure. So if I do 0.1 squared times 0.2, that's what's on the bottom. All right, 0.002, and I do 24 divided by that. Right, so we get a really big rate constant. We get 12,000. So this is a very fast reaction. Now if I think about units, I have m cubed on the bottom because m squared times m is m cubed. And then I have molar per second. So molarity on the top will cancel with one of the molarities on the bottom. So we get m to the -2, s to the -1. That's the same as 1 over m squared times s. Whichever way you represent it is up to you. They mean the same thing. So once you have the rate law, you calculate the value of the rate constant using one of the experiments. Okay, so then part C. So now we're tying in part C and D back to what we talked about yesterday. So part C, how is the rate of appearance of NOBr related to the rate of disappearance of Br2? As soon as you see the word appearance and disappearance, I need you to remember that is when you look at the stoich. When you see appearance and disappearance, that is when you relate it to stoich. So here's where we're looking at the balanced equation now. 2NO plus Br2. So I guess it's NOBr to Br2. Still, it's 2 to 1. So the rate of NOBr is 2 times the rate of BR2. So the rate of appearance of NOBR is twice as fast as the rate of disappearance of BR2. Or you could go the other way. BR2 is half the rate of NOBR. Appearance and disappearance means you're looking at stoic. So now part D is taking it kind of one step further. It says, what is the rate of disappearance of BR2 when NO is 0.075 and BR2 is 0.25? So I'm going to be solving the very end. My answer should be rate of disappearance of BR2. I need to do some things first. Because if I'm using the rate law, up here it says this is initial rate of NOBR. Right? So that means that this is rate of appearance of NOBR. So if I'm solving for rate in this rate law, I'm actually solving for the rate of appearance of NOBR. So I'm going to solve for that first. So I'm going to use the rate law. Right? I'm solving for rate. So rate equals, and we're going to plug everything in. Remember, once you have K, you have K. Until you change the temperature, you add a catalyst. So 12,000 m minus 2 s to the minus 1, that's K, times the concentration of NO squared. Here's NO, 0.075. Times the concentration of BR2, which is 0.25. So let's plug this into the calculator. 12,000 times 0.075 squared times 0.25. Here's what it looks like in my calculator. 12,000, 0.075 squared, 0.25. So I get 16.875. Now I'm going to label this rate of NOBR is 16.875. So m squared molar per second. That's NOBR. Problem wants BR2. So here's what I'm going to do. For every 2 NOBR that's formed, for every 2 NOBR that's formed, we only need 1 BR2. So 16.875 divided by 2, 2 sig figs again, 8.4 molar per second. 8.4 molar per second. So that's kind of tying in, looking at rate laws, right, and kind of paying attention to what the rate is. So this rate, it said it was the initial rate of NOBR. So that was the appearance of NOBR. And then it was just taking it kind of a step further with rate of disappearance. There is one more example. We're not going to worry about that one. That is looking at lots of algebra. So we might worry about that one later. Like that might be a review for right after break. I do want to answer any questions. And then I know there's only about 10 minutes left. I know this was example heavy, but this is the best way to at least start getting acclimated with rate laws. So before we, you guys start just working, I do want to look at kind of ahead, I guess. So all of these examples that we just went through are in the Do Now slides. So you'll notice, for example, here was example 10 that we just looked at. Again, there's only about 10 minutes left, but based on what we just went through, you can now work on mastering up through number 19. So that's about halfway done with mastering. There are lots and lots of practice questions, extra credit questions, and just questions in general to help you through 5.2. I do want you to kind of spend the weekend. There's no weekly review, but I want you to spend the weekend focusing on reviewing the first 2 videos, looking at the examples. If you remember, we're going to have a quiz on Monday. We will go through any questions at the beginning. You'll have a calculator. You won't even need a periodic table and an equation sheet. But if you need extra help as you're looking at examples, remember that 14.1 to 14.3 in the book does go over this first part of kinetics. Over the weekend, if you have questions, you can send them to me. And again, the beginning of class on Monday, we'll kind of do an overview of, we'll have a do now, we'll do some more practice questions, and then, get any questions answered that you might have. So that's all I have. I know we only have a little bit of time left, but you can use this time to work, to ask questions, and then send any questions that you have over the weekend. So you can feel free if you want to leave the meet as you work for the last 10 minutes. That's